So let's move on to, if you have an interest in calculating area under disease progress curve, unless you know how to do it, then we can skip the exercise. You want to see it? So say, for instance, you take Rust notes on 5 dates, day 1, day 8, 15, 20, and 30. And that would be the corresponding score then taken on day 1, on day 8, 15, and so forth. So you can see we went from a 0 to a 90 within 30 days. And that's quite easy to plot. You have time on the x-axis and then disease or rust on the y, and you can get a disease progress curve. Now what we want to do is to calculate the area below that curve, because that will be an indication of the amount of the disease as well as the rate of the disease development. There are other ways as well that Neil can tell you about if you want to use infection rates. But this is a very valuable one to compare different entries or rust epidemics by calculating the area under the curve. Now, if we divide the area under the curve into a series of triangles and rectangles, you can do it by hand, because we all know how to calculate the area of a triangle. It's length times width divided by 2. And obviously the rectangle would be the same, but we don't divide by 2. And we know that value, that's 7. And we know that value, that's 5. So 7 times 5, 35, divided by 2 would give me 17.5 for the first triangle. So we can now calculate all the triangles, all the rectangles, and then add those together, and we'll come up with the area under the curve. And there I did that by hand, so you can see the values. And if you add all those individual values together, you will get a final AUDPC of 1032.5. But that's a very long way of doing it. You can also use this equation. Now, it may look complex to you, but it is not. It's actually quite simple. You take the disease score at day 1, and you add the next score, and you divide by 2. Then you take the time of the second score, you subtract, or you just get the difference in time between your scoring dates. Between day 8 and day 1 would be 7. And then you multiply those two, and you do that for each scoring pair. And I will show you how that works. There's my original data set. So that would be my first data pair between times 1 and 2. So I add a score at the first date plus 5 at the second date. I divide by 2, I get 2.5, and I multiply with the difference in time, which is 7. I get 17.5. So you can see already I'm getting to the same value that I had doing it manually by hand. And so you can calculate the next one. It would be 5 plus 10 divided by 2. That's 7.5 times 7. Again, I have a 7-day difference. It's 52.5. And the same for that pair, and the same for that pair. Again, if you now add all those values, you get exactly the same, 1032.5. So how do we do this? Using Excel. You just have to set up a worksheet where you have time in the first column. The second column would be the difference between the scoring dates, the number of days, the delta T as they call it. And then you have, in this case, 2 varieties, one in blue and one in pink. You have then, just to set up the calculation, you have to add the 2 scores. Then you have another column where you divide the 2 scores by 2, and another one where you then multiply that product with delta T. I suppose you can do all that in one cell if you can program it. Just for explanation purposes, I've got it in different columns. So let's look at Excel. The same data set, day 1, 8, 15, 20, and 30. There would be the time differences between the scoring dates, then variety 1. That would be the 2 scores for the data pairs, 5, 5 plus 10 is 15, 10 plus 65, 75, etc. The division, and then the multiplication. And you can see I get exactly the same value, 1032.5. And if you go down to the individual cells, you can see it's just this very simple formula that's put in. It means A5 minus A4. A5 would be day 8, and A4 would be day 1, so the difference is then 7. So you can just program each of your cells according to what you want to do, divide, multiply, etc. And then your final value would be your area under the curve. Now, variety 2 had much less disease, so just by looking at the progress curve itself, you can see that it must be much more resistant. It's got partial resistance or slow rusting, and it's actually the area under the curve must be, just from looking at the curve, must be much smaller, and indeed it is, 231 compared to 1032.5.
1032.5, what are the units?
That's just a value. Yeah.
It's a square.
It's an index, yeah.
It's an area value.
It's an area value, but it's not square millimeters, or it's just a value. So let's say, for instance, we had a different variety here. We had 5, 20, 40, 80, and 100. And you can see immediately it calculates a new value of 1497.5, and just by looking at the curve itself, you can see it must be more susceptible because it was a much more steeper or a bigger area under the curve. So this is a very valuable index, I think, to use. And if you do this over replications, you can do ANOVAs on this AUDPC. You can use it in the regression analysis, or however you may want to apply it.
What is the acceptable range?
Oh, I don't know.
Acceptable range of,
That I can't tell you. But the first one I showed, I think, would have been acceptable. 230 against 1,000. But you must decide what is acceptable according to your checks.
I mean, they'll have to put a susceptible check along with
Yes.
it and then compare it with.
Exactly. And the resistant check as well.
And a resistant as well, a positive and a
And
negative.
then you can compare and see what is acceptable.
And it is a comparative value.
I normally add the check and then I calculate relative IUDPC.
Yeah, you can also do that. Yeah, that's a good, you often see that.
You can do relative with resistant, but
Yes.
that doesn't really make sense if it's major. So it's better to do relative with the susceptible and then see the difference.
So if you understand what Sajid is saying, he uses maybe average set as his check, and he gets a value of 780, so he sets that as 100. And then all the other AUDPCs are then calculated relatively to 100.
But it depends, I mean, if value is less than 100, it is supposed to be a specific type of resistance. But when it goes 100 to 200, then it has got some 1 or 2 gene combinations. So like that, I mean, what is your interest? That is very important. If you want slow rusting, you will have to fix that range. So then you can select slow ruster out of this.
Well, I think Robert has an article on leaf trust, it's Patan and Paul, where you have identified some ranges. Well, it's not thumb rule, but 2007.
Yeah, we did, we did for each rust, standard length and stripe rust, 3 separate papers, I think, in Ufidica.
Yeah.
And this is a very good measurement, even not for the rust, in the portfolio blight and other diseases also. It can be applied. But the matter is the susceptible variety. How much they have got the AUDPC, and in comparison to other your test entries, how much they are getting. So it depends upon the country to country or person to person, even the place to place, it's very.
Then other thing you encounter sometime, if you very early suckers, you had very So you're not able to get the final reading on those like for 30
Yes.
days.
Yeah.
So I don't know how you transform that. Basically you get another, say after 15 days is 100s. So after 30 days you put 100s again, or it's difficult to.
It's probably not correct, but that's the only way you can do it is to assume it would have been 100 all the way through.